Hi, everybody. Thanks for joining me. Today we're going to start the first of two lectures on sampling distributions. Today will be the introduction, and then the next lecture is going to contain probability questions using sampling distributions. So let's review some terminology. The population is the entire collection of individuals or objects of interest. So the population means everything. We could be talking about things like computer chips. We could be talking about people, but it's every item in a particular group. The sample is a portion of the population that is selected for study, and so it will be smaller than the population. Inferential statistics is the process of using sample information to draw inferences or conclusions about the population. And it's extremely helpful because rarely do we have access to an entire population, and we rely on samples to make conclusions about groups of people. So the use of inferential statistics is very important. So the population is in blue, the blue oval, and imagine the sample is randomly selected from various randomly selected items out of the population, okay, collected into a sample. We're going to start with a simple sampling distribution activity with a very small population. And we're working with a very small population. There's only 5 items in this population because mathematically it's easier to work with this smaller set of values to demonstrate a concept. Once we prove the concept, we're going to apply it to a much larger population and see how it relates. We have a population of 5 patients. They are all receiving physical therapy at a local clinic. The patients are P1 for patient 1 through P5 for patient 5. N, capital N, is the size of the sample, and I'm sorry, the size of the population. In this case, the population size is 5. Okay. Each patient was asked how many hours per week they spend in physical therapy sessions. That's the variable being measured here. The weekly therapy hours are 4, 8, 12, 16, and 20. We're going to put this in our calculator and use 1var stats to find the population mean and population standard deviation of the set of data. So with me, let's go to the calculator, put these numbers in a list, and then get the population mean and standard deviation. Okay, so here we are. Let's press Stat and number 1, edit. And we're going to put in 4, 8, 12, 16, and 20. And we're going to run 1var stats to get our mean and standard deviation. So hit Calc, number 1. We're in L1, leave frequency list blank and calculate. And the mean is specified as 12, even though the symbol is X bar, where we know we're working with a population, so the correct symbol is mu. And the standard deviation is the one for the population. We're going to use sigma X. We're going to take it to 4 decimal places, 5.6569. So we're going to go back to the slideshow now, knowing that mu is 12 and sigma is 5.6569. Okay, so this is what we did on our calculator. Just to recap, mu is 12 and sigma is 5.6569. Now I have a nice visualization calculator set up, DESMOS. It's free for everybody to use, and it nicely can present data in the form of dot plots. I'm going to show you the population in the form of 5 dots because there are 5 items in this population. And we're going to see where they lay on the horizontal axis. And we're going to use DESMOS for a lot of visualization in this lecture. Okay, so what you're looking at here are the 5 items in the population, and there's only one of each item. Remember, there was only one 4, and there was one 8, and one 12, and one 16, and one 20. And so these lines appear in a straight pattern. This is a uniform distribution. There's only one value for each item. Or one, the frequency of each item is just 1. If we had more than one of, let's say, number 4, if we had another 4 in our population, there would be a second dot up here at 2. So the dots show you that we have one of each value. The spread is really symmetrical. We have an equidistance between each point. And we're told that the spread of our distribution is the 5.6569 number that we got off of our calculator. I also have that available here in DESMOS on the left. Using a tool, using a DESMOS function called mean, I can calculate the mean right here and show it visually. So this vertical line here is showing the mean of our population, which is 12. The standard deviation shown here also 5.6569. So that's how we can use DESMOS to visualize the population. We're going to go back and consider sampling from this population. Okay. So suppose that we need to sample from this population because maybe we don't have access to the entire population for whatever reason. So this is a really small example to demonstrate that sometimes it is necessary to sample because you don't have access to the entire population. So let's suppose that we choose to sample 2 patients from our population of 5. And that in that case, lowercase n is 2. And using that sample of size 2, let's find the mean of that sample, which is x bar, and use that mean to estimate mu. So we know mu is 12. Let's see if we can get an x bar that's close to 12. Let's pick a sample of 2 patients. Our first sample, let's look at patients 1 and 2. So from this list, we are going to look at patients 1 and 2. We're going to look at their values and calculate the mean of this sample. So our sample just contains 2 items, 4 and 8, and the mean of that sample is 4 plus 8 divided by 2, which is 6. Okay, so the mean, the x bar, the sample mean for our sample is 6. Now, that's not the only mean that we could have chosen. We could have chosen a different sample. We could have chosen P1 and P3. That's a sample of size 2 as well. So P1 and P3, if we were to calculate its sample mean, 4 plus 12 divided by 2, okay, that would give us 8. That's a sample mean of 8, which is different than a sample mean of 6. So what I'm showing you here is that we can possibly calculate different sample means by picking different samples. Some of them are going to be closer to the true population mean mu than others. So I'm going to show you how we can systematically look through look through all of the look through the population to find all the possible samples. So P1, P2 was the first one. P1, P3 was another one. We can also think about P1 and P4, P1 and P5. P2 and P3, P2 and P4, P2 and P5, P3 and P4, P3 and P5, P4 and P5. And that collection makes up 10. There are 10 possible samples of size 2 taken out of our population of size 5. And this column, the second column, gives all the data values. If you want to take a minute and pause the video, calculate X bar for each of the samples. And you could probably do most of this in your head. We already did the first two together. The first was an X bar of 6, and the second one was an X bar of 8. And if you continue going down, I'm going to show you the answers here. All the possible X bars are listed here. Some of them, like 12, this one for P1 and P5, or this 12, P2 and P4, these two are exactly equal to the population mean. Others, 6, 8, 10, and this 10 are below the population mean, and others, 14, 14, 16, and 18 are all above the population mean. So some of them are further away than others, but they are all sample means, and this collection of sample means has a name. I'm going to first visualize this in DESMOS. I'm going to take these 10 sample means and put them in DESMOS, and then we're going to give it a name. Okay, so if I take my 10 sample means and plot them in a dot plot on top of our population, that's what we have, the orange dots. So I'm going to take them away again and take note of the placement of the orange dots. So notice that the orange dots they span from 6 at the lowest to 18 at the highest. And these up here are there because there are two 10s in the list of sample means, there are two 12s in the list of sample means, and there are two 14s in the list of sample means, so we have two dots. Otherwise, you see them all lie on the same line. There's another thing to take note of. Besides the fact that there's more sample means than there are members of the population, the other thing you should take note of is that the spread of the orange dots is not as variable as the spread of the green dots. So notice that, remember that variability is a measure of the spread of a distribution. The more spread out it is, the higher the variability, which is a measure of the standard deviation. If we take a look at that standard deviation for the population, 5.6569, if I put the sample means on top of that, notice that there's less of a spread. I do calculate the standard deviation down here, 3.4641 for the orange dots, and I also calculate the mean, 12, which is the same as the mean of the population. Okay, so let's confirm that with the calculator. Let's go back to the calculator, and we're going to put in the 10 sample means, and we're going to calculate the mean of all those sample means and the standard deviation of all those sample means. So let's go back into a list, an empty list. Let's choose L2 now, and let's put in the entire collection of sample means. And there are 10 of them. And from this list, let's calculate one var stats. So we're finding the mean, and this is, change this to L2. We're finding the mean and the standard deviation of this group of sample means. And there we are. We're seeing that the same exact mean is what we get for the group of sample means as compared to the group of 5 values from the population. It's the same 12. But we do see that the population standard deviation, 3.4641, is certainly less than the standard deviation of the population, which was visually demonstrated because the points were clustered closer together. The orange points were clustered closer together than the green points. So there's some special terminology that we use when we're talking about the collection of X bars that's in the last column here. This collection of X bars, let's remember what it is. It's the collection of X bars from every single possible sample of size 2. So there's no more than these 10. We've exhausted every single possible sample of size 2. The name of this group is called a sampling distribution. And the sampling distribution has a mean, and its mean happens to be identical to the mean of the population. And we saw that visually. We also saw it with one var stats. The standard deviation is smaller than that of the population. So we saw it when we did it visually. We saw the orange dots were clustered closer together, meaning a smaller measure of variability, a smaller standard deviation. And we saw it with one var stats as well. So here is the population and the sampling distribution in green and orange. The mean goes through the center for both of them. It's 12 for both of them, but the spread or the variability is different. It is bigger for the population than it is for the sampling distribution, and therefore the standard deviation for the population is bigger than the standard deviation of the sampling distribution. So we're going to get started, and let's take a minute and recognize that this relationship between means and standard deviations in populations and sampling distributions always holds true. The mean of the population will always be the same as the mean of a sampling distribution, and the standard deviation of the population will always be greater than the standard deviation of the sampling distribution. So we have some terminology, we have some symbols that we use for the mean of the sampling distribution and the standard deviation of the sampling distribution. Let's get started with the mean first. We're aware that it's identical to the mean of the population, but the sampling distribution is a different set of numbers. So we're going to represent it with the symbol mu sub x bar. Mu meaning the mean, and the subscript x bar, you can think of that as of all the sample means, the mean of all the sample means. And the relationship, and I'll say mu sub x bar for the subscript x bar, the relationship is that the mean of a population is always equivalent to the mean of its sampling distribution. We have this relationship no matter what. So, we saw it with a population of size 5, but it is also true with a population of size 5,000 or 5 million. The mean of a sampling distribution is always the same as the mean of its population. Okay, keeping that in mind, we're going to be able to solve problems involving sampling distributions. Instead of having to go to the calculator and run one var stats on all of the data that we have, we can use this relationship and know that the mean of the sampling distribution is the same as the mean of the population. So the next thing we're going to do is expand our population to something that is more realistic. Populations are often not so small, like like the 5 patients in our example. Let's look at a more realistic set of data for a non-normal population of size 5,000. This non-normal population, this is a snapshot of DESMOS, but I'm going to go back to DESMOS and show this to you more hands-on. It looks like it's pretty skewed to the right, Okay, so it's definitely not normal. It represents the duration of hospital stay for patients in days. So we have short stays all the way down to long stays. Okay. The dark vertical line right here represents the mean of this population of 5,000 5,000 patients, and it's 3.9590. So I'm going to say we randomly select 10 items out of the population, and from that randomly selected sample, I want to calculate the sample mean. DESMOS can do this for us. So I'm going to go over to DESMOS and I'm going to show you what happens if we randomly pick 10 items out of the green data and calculate the mean of those 10 items. Okay, so here we are in DESMOS, and my slideshow had a slightly different appearance. And it's because DESMOS has the ability to view the data as single dots, which are considered to be exact values, versus binned dots, which tends to look a little bit like a histogram. It puts the data into classes and it creates these vertical lines which look like the bars of a histogram. So I can either view it as exact or binned. I'm going to keep it as exact so the dots really look like they're individual items in the population. So here's my definitely not normal population, and I can randomly select 10 items out of it. I've got this function here, d.random. First, let me say what d is. D is the population of 5,000 items. You can see 5,000 element list. You don't have to know how to do this in Desmos. I'm just explaining where the functions are coming from. So we have D representing the population, and then down here, I'm taking 10 random items out of the population and calculating their mean. And on the next line, I'm making a vertical line to represent that mean. Okay, so there is that vertical mean, that vertical line with the value 3.534 is pretty close to the population mean of 3.9504. So I randomly selected 10 items and found their sample mean, and that's its value, 3.534. Now I can do that again using this randomization, like almost like a shuffling icon. It selects a different 10 items out of this population and calculates its sample mean. So I'm going to show it to you. Okay, so this one's a little bit smaller. Its sample mean now 2.722. And I could keep doing this. I could keep randomizing and getting different sample means. 2.985, 4.175. I'm looking over here, by the way, to see the sample mean. 2.117. Okay, and this one's got a little bit higher, 5.669. So if I keep doing this, you'll see that the sample means that I'm randomly selecting generally stay close to the population mean. You see where that line is near the 4, that green line. My red line isn't straying too far away. I mean, it can get a little far away. Okay, here it's getting 1.4 on the left. And then we did see it go up almost to 8 on the right in one of these randomizations. But for the most part, it's staying pretty close to 3.95. And the reason for that has to do with the same reason why the orange dots as compared to the green dots in our first example, the orange dots were closer to one another. There was less variability in those orange dots. And that's what we see happening here. There's less variability in our sample means as compared to our population data. They're kind of staying pretty close to the green vertical line. So let's consider some questions. Why do we think the sample means seem to stay near that vertical line? They seem to stay between about 2 days and 8 days. Besides that, what do we notice about the variability? The spread of the sample means that are calculated from these random samples. How does it compare to the population variability? And what do you think would happen if we were to increase the size of the sample from n equal 10 to n equal 30 or n equal 80? Do you think we'd see anything different when we calculated our sample means? Well, when we calculate sample means, extreme values in the population are smoothed out. So think about this. When you take a single point, a data value from a population, it could be anywhere in that population. It could be very small, it could be very large, it could be somewhere in the middle. We know by the looks of the population, it's probably closer to the left because most of the data is closer to the left, but it could be anywhere. When you do that 10 times and you calculate the sample mean from 10 of those data points, you average those values together, and the averaging process naturally reduces the impact of any one extreme value. When you have a very high value in a set of 10 numbers, it's kind of smoothed out that high value. You'll never get an average as high as the highest value because it's incorporated with the other values, which bring it down. So that's the result of averaging. Same thing with thinking about a very low value. If you have a very low value, in your set of 10 randomly selected items from the population, then the sample mean will never be as low as that low value because it's being averaged with other values that aren't as low. So mathematically, you're always going to get a sample mean that's not as far out to those extreme values. Considering the lengths of hospital stays for patients, if you look at individual patients, some may stay for 1 day, others may stay for 30 days. There's a lot of variability in the original population. But if you take random samples of 10 patients and calculate the average length of stay for each sample, the extremely short or long stays will have less influence on the sample mean. And that's what we see happening visually with our sample means. This makes the sample means more consistent and less spread out than the original population. So that's why sample means were hanging out between 2 and 8, because averages naturally cause them to be closer to the mean of the population rather than spread out. Okay, next thing we're going to do is go back to DESMOS, but we're going to look at what would happen after taking samples of different sizes. So we saw samples of size 10, and then we're going to look at samples of size 30 and samples of size 80. Okay, so here I am back in DESMOS, and my red line was the mean of the sample, the randomly selected sample. I'm going to take that away. Okay, so we're back to looking at the population here, and the mean of the population is the green line. And there's our full population. Okay, so if I were to do those samples of size 10, I wanted to just do this before changing the sample size. I want to keep the sample size 10, but I want to do it 1,000 times. So instead of just one sample of size 10 and looking at that single sample mean, which is what I was doing here before, let's take 1,000 samples of size 10 and plot the sample means. Okay, so 1,000 samples of size 10. This is what I'm doing here. I'm taking a random sample of size 10. I'm taking its mean and I'm doing it 1,000 times. Okay, and I'm putting this in another distribution. If I plot this distribution, it's going to appear in black here. You're going to see the shape of the sampling distribution for samples of size 10. It's the dots in black. As we expected, the variability of the black distribution is smaller than the variability of the green distribution, for sure. And I'm going to also show you the mean of the black distribution. Remember, the black distribution is a sampling distribution for sample size 10, and the black line represents the mean of that distribution. So the black dots, there are 1,000 random samples taken out of the population of size 10, and these are the sample means. If I randomize this, I'm going to see the black dots kind of move around a little bit, but not terribly change their location. Okay, I'm going to keep doing this. They move around, but they don't change their variability so much. They don't change their location so much. There are different values, but they're generally in the same place. And also, if I keep doing this, you'll see the mean of that sampling distribution change too, 3.878. And then the next time I do this, 3.9455. So the sampling distribution mean is changing each time. And okay, just a second. So the reason why the mean of each sampling distribution that I generate here, the reason why it's not exactly the same as the mean of the population, which remember the mean of the population is 3.95 up here. The reason why it's not exactly the same like our relationship showed us earlier is because I'm doing this only 1,000 times. My sampling distribution only contains 1,000 items instead of every possible sample of size 10. So there's far more samples of size 10 that can be taken out of the population. I only have 1,000 of them. So if I did this more, I would eventually see that the mean of the sampling distribution was the same as the mean of the population. Okay, but let me keep going now. Now that we see what the sampling distribution looks like when samples are size 10, let's take a look at, I'm using the same syntax here to find samples of size 30. Taking the mean of a random sample of size 30, doing it 1,000 times, and creating a dot plot out of it. And in orange, you are going to see 1,000 sample means, but these sample means are taken from samples of size 30, whereas the black were samples of size 10. I'm going to do this. I'm going to show you the mean of the orange data. Okay, 3.95, very close to the population mean. And I'm going to shuffle things out again. Different 1,000 samples, a different 1,000 samples. I could keep doing this. It's roughly going to always appear in the same place, although they move around just a little bit. That's samples of size 30. Next, I'm going to do the same thing with samples of size 80. 1,000 random samples of size 80 taken from the population and plotting it in a dot plot creates a sampling distribution that looks like these purple dots here. Okay, so now I clearly see a shape forming, and if you didn't see it already with the orange, you should definitely see it with the purple. We see the formation of a bell curve, the normal distribution. And that's not an accident. That actually will happen every single time. Let's back up a little bit. No matter what shape population you start off with, like here we started with something that was definitely not normal in green. Once you start taking samples out of that population, the sampling distribution will automatically be normal if your sample size grows large enough. Okay, so let's go back. Green, the green was a population. The black samples of size 10, kind of forming a little bit of a bell, but not not clear at all. Okay, that's the black one. The orange one is definitely more of a bell curve, and the purple one, absolutely more of a bell curve. Okay, so we see the shape definitely changing as n grows larger. The other thing that we see changing, take a look at the spread of data. The spread of the black data is more variable. You see it go out further, and the spread of the orange data comes in even closer, and the spread of the purple data comes in even closer. The variability of the distribution also changes as the sample size increases. We see here, as the sample size increases, the variability decreases. And that is measured by the standard deviation of the sampling distribution. We're going to give that a name in a minute here. So we see variability changing as n increases. So our original population, 5,000. When we took a sample of size 10, our sampling distribution looked like the one here in black. And then when n was 30, it looked like the one in orange. And then when n was 80, it looked like the one in purple. And we certainly definitely see a bell with the one in purple. So as a rule, when the sample size increases, variability decreases. Going back to that picture on purple, you see things were more spread out in the population, smaller variability in black, even smaller variability in orange, and the smallest variability in purple. The spread is smallest in the purple distribution with the biggest N. The measure of variability in a sampling distribution has a special term. It's called the standard error, and it uses the following notation. It is always smaller than the standard deviation. So the standard deviation of the population is sigma. The standard error is sigma with a subscript x bar, or sigma sub x bar. And it has a formula. We use sigma divided by the square root of n to calculate the standard error. So a problem has to provide you with sigma, and it has to provide you with the sample size, and using those two numbers, you can calculate the standard error. The mean of a sampling distribution, mu sub x bar, and the standard error of the sampling distribution are going to help you answer probability questions in the next lecture. Let's look at some examples. Hospital length of stay. The average hospital length of stay for patients in a certain city is 5 days with a population standard deviation of 2 days. So this problem provides us with a mean of the population and a standard deviation of that population. If you take random samples of size 10 patients, find the mean of the sampling distribution using the proper symbol. Find the standard error of the sampling distribution using the proper symbol. Okay, so this is what was given. Take out what was given, write it in the margins of your notebook, and the mean of the sampling distribution first. We're going to apply the relationship that the mean of a population is always equivalent to the mean of a sampling distribution. And so since we know the mean of the population, we automatically know the mean of the sampling distribution. It is the same value. It's 5 days. But the proper symbol to use for the mean of the sampling distribution is mu sub x bar. The standard error of the sampling distribution, we're going to apply the formula. So we're going to take the mean of the population, the standard deviation of the population, 2, and divide by the square root of the sample size, n. And I'm going to take you to the calculator because I don't believe we've used standard, I don't think we've done square root yet. So let me show you where that is on the calculator. Okay, we're going to put in 2 and divide by, and we're going to use the second key and the x squared key. Above it is in blue the square root symbol, 10. 0.6325. Okay, 2 divided by square root of 10 is 0.6325. So we're using the proper symbol and we're calculating the standard error. Problem 2, emergency room wait time. The average emergency room wait time for patients is 90 minutes with a population standard deviation of 30 minutes. If you take a random sample of 16 patients, find the mean with the symbol of the sampling distribution and find the standard error with symbol of the sampling distribution. Same as before. Okay, so extract what we have given us, what's been given to us from the words of the problem. We have the mean of the population, the standard deviation of the population, and the size of the sample. We're going to calculate the the mean of the sampling distribution, which is the same as the mean of the population, but you want to make sure the symbol you use is mu sub x bar. That's 90. And the standard error of the sampling distribution, you're going to apply the formula and take 30 divided by the square root of 16. Okay, 30 divided by 4 is 7.5. So you use the proper symbol for the standard error and the value out of the formula 7.5. So recalling what it looked like when we changed n in a sampling distribution, let's start with the original population, pop on the left, and then we had 3 versions of sampling distributions as n got larger. Besides becoming less variable, because we saw the x bar, sigma x bar is going to be different in each of these cases. It's going to get smaller because when n is 80, the denominator will be biggest. Let's look at the mathematics of this formula here. When you put a large denominator into a fraction, the whole fraction decreases. So when we put n equal 80 as opposed to n equal 10 into this formula, the fraction decreases, the value decreases. That means the standard error decreases, the variability decreases. And that's what we get in the purple distribution. So the shape of the distribution also changes. In black, I kind of see something starting to be like a bell. In orange, yes, it looks pretty close to a bell. And in purple, it's definitely a bell. So even though the population that we started with was not normal, we see that if we make n big enough, the sampling distribution does become normal, which is really a powerful tool. With a normal looking sampling distribution, you can use all the tools of a normal distribution, namely normal CDF on the calculator to calculate probability problems. And this opens up a whole world of possibility. Without needing to go to the population for data, we can just use a well-sized sample. So that's going to bring us to the central limit theorem. We're going to abbreviate the central limit theorem with CLT in some of the notes here. The central limit theorem defines the shape of a sampling distribution under different scenarios. We saw that when n was 10 in the previous picture over here, this really doesn't look too normal. It looks like it may be going in that direction, but it's not normal. So using this sampling distribution would not work if we wanted to use normal CDF. So here's the criteria for making that decision. If the population that you're sampling from is already normally distributed, the sampling distribution of a sample of means of, sampling distribution of sample means will also be normal regardless of the sample size n. So we didn't do that example because the population that we worked with in this problem was skewed right. It was definitely not normal, so we didn't have a problem that falls under the category of scenario one. But if we started with a population that was normal to begin with, then no matter what n we chose out of that population, the shape of our sampling distribution would come out looking normal each time, no matter what n was. So even if you have very small sample sizes, you still will have a normal shaped sampling distribution. In this example, we have a population of blood pressures and we're told that it's normally distributed. We take samples of size 5 from the population. Is the sampling distribution normally distributed? And the answer is yes, because scenario 1 holds. The population was normal to begin with, so the sampling distribution is automatically normal, no matter what the n is. Now, the second scenario is going to apply to what we just saw with our skewed right distribution. If the population is not normally distributed, so if we have a skewed distribution or bimodal or just something that is completely odd shaped that doesn't have a name, it's okay. The sampling distribution of sample means will still be approximately normal if the sample size n is more than 30. So that proves what we were talking about when we looked at the various sample sizes. When it was n equal 10, the black graph wasn't really too normal. And then when it became n equal 30, it looked pretty normal. And then when it looked n equal 80, it was certainly normal. So our rule of thumb is that we're going to assume that n has to be more than 30. If it's more than 30, we're going to say for sure that the sampling distribution looks normal. If it's less than or equal to 30, the shape that comes out for the sampling distribution is going to be unknown. And if it's unknown, you're not going to be able to conduct probability analysis on it. The population of hospital wait times is skewed right, which is not normal. You take samples of size n equal 40 from the population. Is the sampling distribution normally distributed? And the answer is yes, because n is greater than 30. 40 is greater than 30. The sampling distribution is normally distributed. Now, if you have a scenario where n is less than or equal to 30 and the population is not normally distributed, you won't be able to do a problem like that. And so most of the problems that you'll see me ask you in this unit are all about n's that are greater than 30 if the population is not normal, because if it's not, then you won't be able to do the problem. Okay, so why does this happen? When you take an average from larger samples, extreme values tend to cancel out, creating a bell-shaped curve. And this happens more and more the bigger the sample is. Let's look at central limit theorem problem number 1, blood pressure readings. A hospital is studying the systolic blood pressure level of its patients. It's known that the population mean blood pressure is mu equal 120 and the population standard deviation is 15. A hospital selects random samples of 40 patients. Find the mean and standard error of the sampling distribution. So we're going to do what we had done before. Let's find mu sub x bar and sigma x bar, the standard error. Based on the sample size and the central limit theorem, explain whether the sampling distribution will be approximately normal. So the first part is like before. We just take what we have been given in the problem and calculate the standard error. The mean of the sampling distribution is relatively no work at all. You just are stating that the mean of the sampling distribution is the same as the mean of the population using the proper symbol. The standard error, you're applying the formula. You're going to take this population standard deviation and divide it by the square root of the sample size. 15 divided by the square root of 40. And here that's 2.3717. So that's the first part of the problem. And then now let's talk about the shape. We have an n that's greater than 30. And because of the central limit theorem, n equal 40 is greater than 30. The central limit theorem does apply, and the sampling distribution of the sample mean will be approximately normal, no matter what the population's shape was. Okay, so since this is the case, we have a normally shaped sampling distribution, we can answer probability questions based on this problem, this application. The sampling distribution would be approximately normal. The center is where we label the mean of the sampling distribution, and along the horizontal axis on the left and the right are other possible sample means. Okay, all the other possible x bars are listed on the horizontal axis. And from our very first example in this lecture, we saw how some sample means are really close to mu sub x bar and other sample means are further away. Altogether, they are the sampling distribution. Okay, let's look at another problem. We're measuring or studying the number of daily medications taken by elderly patients. The average number of medications taken per day, and we're given a mean of 7 and a population standard deviation of 3.5. We have a shape. We're told that it's skewed to the right. And like in the last example, we weren't even provided with the shape. So as soon as we knew that n was greater than 30, though, the unknown shape, we knew it was going to be normal. In this case, we have a distribution that is also not normal, skewed right, and we're using samples of size 10. Okay, so a skewed right distribution, number of medications, this is what it means. We have most of our patients taking somewhere over here and just a few patients taking a lot of medications. So it's skewed to the right. We have samples of size 12. We're going to look at the mean and standard error, and then we're going to determine the shape. Will it be approximately normal, and why? So the mean and the standard error are 7 for the mean of the sampling distribution, and the standard error is 3.5 divided by the square root of 12. You're going to get 1.0104. Okay, and just remember that our standard error is always smaller than the standard deviation of the population. So there's a check on the reasonableness of your answer. You should always be getting a standard error that's smaller than sigma. And now, as far as the shape goes, since we have a small sample and it's less than 30, and we have a population that is not normal, it is skewed to the right, the sampling distribution of the sample mean will not be approximately normal. We do not have a normal sampling distribution. In order to fix this, we would have to make n greater. N equal 12 is just too small. We'd have to make n greater to achieve a normal distribution and do any sort of kind of probability analysis on it. So we say the shape is unknown, and we just need to make n bigger if we're to do this problem. So your homework is going to have a few questions about shape, like these. It's going to have a few questions where it's asking you to calculate the mean and standard error of the sampling distribution. And it's probably one of the easiest homework assignments in a while. So you should be able to do this relatively quickly. This is setting us up for the probability questions that we are going to see in the next lecture. So I hope this was helpful. And if you have any questions, email me, and I will see you at the next lecture.